All right, guys, I'd like to talk about, I'm actually going to come down here to property 5 first. It says division of like bases, okay? And kind of walk through why this rule works, okay? So with multiplication of like bases, you did what with the exponents? Who? Oh, sorry. So if I do multiplication of like bases, you do what with the exponents? We add them. Okay, that was first property we talked about yesterday. If we're going to divide like bases, what do you think we do with them? We subtract them. Okay. Now we're going to subtract numerator minus denominator. Okay. And the reason for that, let's talk about this. Let's go. Let's say we have 2 to the 4th divided by 2 to the 6th. Okay, I'll say we start with that. What does 2 to the 4th really mean? Good. 2 times 2 times 2 times 2, right? What does 2 to the 6th really mean? Okay. So then, because these are all multiplication, okay, we can do this. We can go 2 over 2 times 2 over 2 times 2 over 2 times 2 over 2. Okay, so that's 4 2's from the top. And there's no more 2's up there to go along with the remaining 2 2's on the bottom, right? Does that make sense? But can I do this and not change the top? So then the remaining ones would be 1 over 2 and 1 over 2, right? What is 2 divided by 2? 1. 1. 1. 1, right? Property side. So those all go to 1. So now I have 1 times 1 times 1 times 1 times a half times a half. So all those 1's don't really matter, right? When I'm multiplying. And now I get 1 times 1 up top. And I get 2 times 2 on the bottom, but I can rewrite it that way, can't I? To demonstrate the property. Okay. So here we see basically what we're seeing here is that we're canceling these like ones out, right? Okay. And now to get this 1 over 2 squared, okay, we started with 2 to the 4th over 2 to the 6th. What we're going to do is we're going to ultimately find out where is the largest exponent. It's in the bottom, right? Okay. So those 4 that are in the top, those 4 are going to cancel with 4 that are down here. And we're left with 2 squared. Does that make sense? And isn't that just taking that 6 minus that 4? Does that make sense? And because the 6 was bigger and it was in the bottom, when we do the subtraction, the result stays in the bottom. Okay? We're going to see another rule here in a moment that helps us realize that if I would have just gone, like our rule says, 2 to the 4th over 2 to the 6th, and did it this way, 2 to the 4 minus 6, that gives me 2 to the negative 2. Is that correct? Does that make sense? Okay. Well, do me a favor real quick. Grab your calculators. Type in 1 divided by 2 squared, like that. Okay. We get 1/4. Okay. Obviously, that's 1 divided by 4. Or type this in, 2 raised to the, where is my caret key here? Negative 2, like that. Does it give me the same result? Okay. So 2 raised to the negative 2, 2 raised to a negative exponent is the same thing as basically making that negative exponent positive and putting that thing in the denominator underneath 1. And we'll talk about that rule here in a moment. Yes? That's just the way that you, I mean, they're the same. I don't know, like because that top one, because of the division that you're using, is probably the reason it changed it to a decimal instead. Let's do this. Let's go. Let's go 3 to the 8th over 3 to the 5th. Okay. Now, how many 3's would you have being multiplied out on top? 8. How many would you have being multiplied out on the bottom? 5. How many total would cancel each other out? 5, right? Okay. So you would be left with 3 on top, correct? 3 times 3 times 3. Okay. Or can't I rewrite that as I take the bases are the same. So now I'm just going to take the exponents and go 8 minus 5. It gives me 3 to the third that way. What is 3 to the third? Anybody know? 27. 3 squared is 9. Multiplied by another 3 gives me 27. Is that something we can do? Okay. So here's my question. What is x raised to the 0 power? What does that equate to? Not 0, because remember, it's repetitive multiplication. It is 1. Why? I mean, there's a coefficient of 1, but x could be anything. So basically what I'm asking is, so when x can be, x is a variable, so I could be asking, x could be 1, so 1 to the 0. X could be 2, so 2 to the 0, or 3 to the 0. No, these are equal. Like if I put a slash to that, means they're unequal. But they're equal. If I take my calculator, take your calculator, and type in 2 raised to the 0 power, or change that to 12, or change it to 122, or that number. Still 1, right? But why? Does anybody know why? Because you've been taught in Algebra 1, you were probably told, hey, anything raised to the 0 power is 1, and that's what we're going to use, but never really talked about it. What will, if I had, let's say we go with 4. I go 4 to the 6th divided by 4 to the 6th. Okay, that is 4 times 4 times 4 times 4 times 4 times 4, right? And each one of those cancels, right? And when we say cancel, it doesn't mean they disappear. It means they turn into a 1. And we multiply a bunch of 1s, 6 1s essentially, what do we get? 1. But how does that tell me that 4 to the 0 is 1? If we're dividing like bases, what do we do with their exponents? We subtract them. Okay, that's what this rule here said, right? If we're dividing like bases, we subtract the exponents. So our exponents were both 6. We know that this in one route gets us to 1. So if this rule is true and it gets us to this, those two things must be equal as well. Does that make sense? Okay. So that is the reason, that's the logic why 4 raised to the 0 or 5 raised to the 0 or anything raised to the 0 always turns into 1. Okay? And so that's, like in my opinion, I think there's two ways to teach algebra. One way, teach you to be a robot. Teach you to be a calculator. Say, do this step, do this step, do this step, get an answer. Okay? The other way is to teach you why those steps work. I like to teach that way because I think if you understand why something works, okay, then you're going to be a little bit more self-sufficient down the road with your algebra. You've all heard the phrase, give a man a fish, feed him for a day. Teach him how to fish, feed him for a lifetime, right? It's the same thing with algebra, okay? Show you how to do something and you be a monkey see, monkey do type mathematician, then you're only going to be able to do the problems that you've seen, okay? But if I teach you the underlying principles of why we are doing the things that we're doing, and you should be able to approach any of the infinite problems that you may ever encounter and be able to navigate them. Okay? So that I think that's important to be able to see that recognition. Okay? So let's do some more examples here of division. Let's say that we've got a squared b to the 5th over a b x. Okay. Now, you don't always probably do this, and I think as you get more and more proficient at this, you probably won't ever write it this way. But when I have a product divided by a product, because the associative property, commutative property, all that stuff, we can actually rewrite this as, I can take the a squared and write it over any one of these three things down here. Which one would make most sense to write it over? The a. I can take the b to the 5th and write that over any one of these down here, except for the a now, because I've already used the a, right? So I'd probably use b. Okay, now the x doesn't have anything to go with, so it's always a 1, right? I like to do it that way because now it just basically takes this problem and breaks it down to 3 simpler problems. What am I going to do with those right there? What's that going to turn into? A to the 1st, right? Okay. Because I'm going to take the 2 minus the 1. That's going to leave that number a to the 1st in the numerator. What's this going to lead me to? B to the 4th. Okay. Now these are not like bases, right? So I'm not going to do anything there. I'm going to have 1 over x. Well, these are, when I multiply these things, multiplying fractions, straight across the top, a times b to the 4th times 1 is a b to the 4th. And across the bottom, it's 1 times x. So it's x. Okay? That's the logic. Okay? But like I said, I don't think a whole lot of times you're going to do that. I think what most people are going to do is say, okay, a's with a's. Okay? So if a is with a, so that a and that one cancel out, leaving me a to the 1st, right? B's with b's, so that one's going to cancel out with that one, leaving b to the 4th. And the x doesn't cancel anything out, so then I'm just going to rewrite this as a to the 1st, b to the 4th over x. But the reason we can do that, we can basically, even if they're not on top of each other, so eventually you might see something like this where it says like x squared y to the 3rd r over, let's say r, y, let's go r, x, y squared. And I want to simplify that. These two don't line up on top of each other like the a's did in the last one, right? But because of multiplication, we know we can rewrite those, so we can flip-flop those two if we wanted to, correct? rxy squared is the same thing as xry squared. So a lot of people won't rewrite it, and they'll just say, okay, those two will cancel with that one, leaving me a 1 there, right? Well, yeah, we'll get to that. That's going to be the next property. We can go y squared. Those two will cancel with those and leave me 1 there. and r to the first and r to the first cancel out completely. So this just leaves me with xy, right? Does that make sense? Okay. What if we have something like, let's go a cubed b squared over a to the fifth y. Okay, now, if I'm canceling, if I want to use that approach instead of the subtraction, because subtracting and canceling is really the same idea here, where would the a's be left? Be a squared, but they're going to be left on the bottom or they're going to be left on top? They're going to be left on the bottom. Because if I think about this, if I expand this, it'd be a times a times a, b times b on top. On the bottom, a times a times a times a times a times y. Cancel, 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 cancel. You're left with two a's on the bottom, right? So it'd be a squared on the bottom times y, b squared on the top. Does that make sense? So getting to what Maya was asking about, she said something about negatives, right? About flipping sides. If I were to just look at, let's just look at a cubed over a to the fifth. Okay, that is a times a times a over a times a times a times a times a. Cancel, 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 cancel. Leaves me 1 over a squared, right? Okay. But if I do the subtraction that this property said we should do, m minus n, it's top minus bottom, right? The subtraction says we should rewrite this as a to 3 minus 5, right? What's 3 minus 5? Negative 2. But all these things are equivalent formats. They're all okay to say. So those come together and tell us that a to the negative 2 is the same thing as 1 over a squared. And a to the negative 2 is the same, I can put it all over 1, right? So we see that a to the negative 2, if I don't like negative exponents, which that's just kind of in general, mathematicians, for whatever reason, have said we never like to write an answer with a negative exponent. Okay, it's kind of like we don't write answers as 2/4. We don't write answers with like radical 9 in them because they can be simplified. So a to the negative 2, we don't like that. So what they say is you take anything that has a negative exponent, you're going to grab the item that is directly in front of that negative exponent. So you're going to grab the a. And you're going to take that object and that exponent and you're going to put it in the denominator. And once it jumps across the division sign, that is going to make that exponent change signs. Does that make sense? Okay. So that logic, though, allows us, because of what we can do with proportion. This is a proportion, which just means that we have an equation that the left-hand side and the right-hand side are exactly the same. Think about this. If you cross-multiply here, you guys know proportions, right? Cross-multiplying. In a proportion, if I cross-multiply, 1 times 1 in this case should equal a to the negative 2 times a to the positive 2, right? Is that true? What do I do with my exponents when I multiply like bases? What was the first property we talked about yesterday? Like bases, you do what with those? You add them. So what's negative 2 plus 2? 0. Is that a true statement right there? Yes. So that means this is true. Okay. Now, if we have a proportion, what we're allowed to do with proportions is actually take the reciprocal of this one and take the reciprocal of this one, and that is also true. And what I'm trying to show you here is that if you have a negative exponent in the top of your fraction, you can move that term to the bottom of your fraction and make the exponent become positive. Does that make sense? If your exponent starts in the bottom of your fraction and it's negative, you can take that exponent and the object that is attached to and move that to the top of the fraction, and it becomes positive. Does that make sense to everybody? So, examples of where we would use that. If they give us something like a to the negative 3, b to the 5th over c to the negative 2. How would you rewrite this? Is this a to the negative 3 going to stay where it's at, or is it going to move? If we don't like negative exponents, though. Okay, so a to the negative 3 is going to go to the bottom. It's going to become a to the positive 3, right? What about b to the 5th? Is that going to go anywhere? Stays there? Okay, so c to the negative 2, we don't like that negative exponent there. So it's going to go up to the other side, and it's going to become positive. Does that make sense? Okay. Now, what you can do with those, or what you'll see with those, is things like this. Let's go like a to the negative 4th, b to the 6th. Let's say a to the negative 3, b to the negative 2. Okay. I personally, I don't like canceling negative exponent, like a to the negative 4th. That doesn't really make a whole lot of sense to me. And canceling with a to the negative 3rd. Okay. I don't like subtracting negative numbers. Okay. So what I'm going to do before I do any cancellation with my variables, because there's like bases here, right? Before I do anything, I'm always going to make sure that I rewrite my problem with positive exponents. So what are you going to do with that thing right there? Bring it down. So it'd be a to the 4th down there, right? What are you going to do with that b to the 6th? Keep it up top. What are you going to do with this a to the negative 3? Up top. And now we're going to do this b to the negative 2. You can put it on top, right? Okay, so now remember what your division bar does from chapter 1. It's a grouping tool. So it's just like parentheses. So we got some stuff up here that we can mess with, right? What's b to the 6 times b squared? Careful. You're right, you need to mess with these exponents, but you add them. So b to the 8th. And you've got a to the 3rd, right? And now underneath would be a to the 4th. Now what can you do? And where are you left with an a? Is it up top or on the bottom? It's on the bottom. The a to the 1st on the bottom, right? That kind of makes sense? Change my personal preference and my suggestion to you is every single time that you see a problem that starts with a negative exponent, or in some manner you generate a negative exponent, immediately change it to a positive exponent. Okay. Let's look at a pattern here real quick to help emphasize this negative exponent stuff. Yes. All right, so if I take, I'm going to create a chart here, okay? And all I'm asking, what is 2 to the nth when n is 1? So what is 2 to the 1st power? 2. And now I'm going to ask, okay, what if the exponent is 2? What's 2 squared? 4. What is 2 cubed? 8. Let's go a little bit further to kind of prove this. Let's go, what's 2 to the 4th going to be? 16. The next one, 2 to the 5th, will be 32. What am I doing each time? I'm doubling, multiplying by 2, right? Each one of them, you guys remember back to early on when we looked at tables, and tables could allow us to recognize relationships between what the rule was that was occurring. This is another way of doing that, or another use of those tables. So I'm multiplying by 2 each time. Let's come over here. We'll just do 3 to the end. So 3 to the first would be 3. 3 squared would be, careful, 3 squared 9. 3 to the third would be 27. 3 to the fourth is 81. And 3 to the fifth is 243. What am I doing each time there between successive tripling it? Multiplying by 3 every time, right? Okay. So let's do this. You usually wouldn't write it this way. This is kind of weird to write it this way, but I'm going to start with my stuff on the bottom. And I'm going to start at, let's just go 5, 4, 3, 2, 1, 0, -1. You might want to put a -2 in here as well. Okay, so working our way from the bottom upwards. Now, so I'm just going to take this 5 and put it in here. So we've already done this. 2 to the 5th would be 32, right? 2 to the 4th would be 16. 2 to the 3rd. 2 to the 4th. 2 to the 1st. Okay, so here's where I'm trying to get us to see what we're doing here. What do I do to go from 32 to 16? Divide by 2. 16 to 8. Divide by 2. Divide by 2, right? Divide by 2. What am I going to do the next one? Instead of saying what 2, instead of you ask or me asking what 2 to the 0 was, and we go off a proper we already know, let's use this pattern. Don't I take this number here, just like I've seen this pattern here, and divide by 2? What's that going to give me? 1. So we see then that if n is 0, we have 2 to the 0. 2 to the 0 equals 1. Does that make sense? Okay, so now what if I want to go to this one? What am I going to do with that 1? Divide by 2. What's 1 divided by 2? Be 1/2, right? So we see that 2 to the -1 is the same thing as 1 over 2 to the first. Does that kind of visually confirm the idea of taking the negative exponents and putting them in the bottom? We can do it again. 1/2 divided by 2 gives me 1/4, and there we see that 2 to the -2 then is 1/4, but 1/4 is the same as 1 over 2 squared. And get rid of that negative exponent, we can put it in the bottom like that. Okay, so dealing with negative exponents, you're going to take them and put them in the opposite position in regards to the division sign. If they're in the numerator, they go to the denominator. If they're in the denominator, they go to the numerator. Okay. The last rule I want to talk about, we've dealt with this with multiplication. If we had, it was up here, if we had something like this here, if we had a product of things raised to a power, okay, we call this a product of powers raised to a power. We simply took that m and multiplied it by the exponent here with the a, took the m and multiplied it by the exponent of t, so that is attached to b, and it gives this thing here, right? Okay, so we just distribute that outside exponent. It's really the same thing here when we have division. Okay, I'm going to tell you, if I've got division raised to a power. So you're going to take that and you're going to multiply it by the s. You're going to take that and multiply it by the t, and that's going to generate this. Does that make sense, everybody? And the reason for that, think about this. If I had, let's just go with an example here. Let's say I have a squared b to the third, and we want to raise all that to the fourth power. But what that means to us is that we have, working our way from the outside in, we have a squared b to the third multiplied by itself 4 times, right? Okay, so that's one way of rewriting that, targeting that power of 4 first. Then I can take each one of those and rewrite a squared as a times a, and then b cubed as b times b. I'm going to cheat. Control C, I'm going to cut and paste these. So there's the second one. Dumb where it pasted it. There's the third one. And there's the fourth one. Does that kind of make sense? So how many total A's would I be multiplying together here up top? 88. And how many B's? B to the 12th. How can I go from this here straight to there? I want to take these two numbers and multiply them. That gives me my 8, right? I distributed that 4 essentially to those exponents. Okay, so I'll take that 4 then, multiply by that 3, it gives me my 12. Okay. When you're done with every problem, okay, just kind of in general, every problem should have, I don't know where my notes went, every problem, when you're done, should have no negative exponents, okay, and there should never be a repetition of a variable or term in the numerator and the denominator. Okay, so if I've got A's in the top in my answer, there should be no A's in the bottom. Okay, if I have 3's in the top in my answer, there should be no 3's in the bottom, and vice versa. If I've got X's in the bottom, there should be no X's in the top when I'm working with fraction work, because that tells me there could still be cancellation occurring if I've got the same variable on the top and the bottom. Does this kind of make sense? Okay. You've still got that assignment. I called it laws of exponents or exponent rules or something like that in Math Excel. That's going to be due, not due tomorrow, it's due the following day. Okay, so I'm thinking Thursday would be a quiz day. All right, Friday we don't have, Friday's an e-learning day. But I think we've got enough things here, and I want to give you a little bit more time than what they're allowing us to use for Friday. So Thursday we're gonna see what we know about radicals, see what we know about some of these exponent stuff. Okay, it will be open notes. Bring your notes. Is it the same vehicle, 4 kids, or just completely separate?